Hello students, we will continue with our last unit, that is finite element method. We have seen in the previous session that what does the finite element method means and what are the applications of the finite element method. Okay, and we'll continue the same unit with as I told you, this last unit is basically whole theory part. So we'll continue first it with, and we'll end up with one numerical, and we're done with this last unit. Okay, so isoparametric, superparametric, and subparametric elements. Okay, so what does this means and what does the shape function? So we are in the second half part of the unit, that is shape functions. Okay, so we have seen in the finite element analysis with isoparametric elements, shape functions are used for defining geometry as well as displacement. If the shape functions defining boundary conditions and displacement are same, the element is called as isoparametric element. So see this first part. Okay, so if shape functions defining boundary condition and displacement are same, the element is known as isoparametric elements. So see, these circles are nodes for defining the geometry, and rectangles are used for defining the displacement. Okay, so here the displacement and boundary conditions are same, so this type of element is known as isoparametric element. Okay, then next is superparametric element. So the elements in which more number of nodes are used to define the geometry compared to number of nodes used to define the displacement is known as superparametric element. So here in this case, nodes are used more for to define the geometry. Okay, so you can see here the circles are more as compared to the squares. Okay, squares are used for defining the displacement and nodes are used to define the geometry. So the element in which more number of nodes are used to define the geometry as compared to number of nodes used to define the displacement is known as superparametric element. Okay, you can see here in this diagram. Now next is subparametric element. The elements in which less number of nodes are used to define the geometry as compared to number of nodes used to define the displacement. So super parametric element, where we have seen there are more number of nodes, and in subparametric element there are lesser number of nodes are used to define the geometry and higher number of nodes used to define the displacement. Okay, and superparametric and subparametric element are exactly opposite to each other. Okay, so this is the isoparametric element, subparametric element, and superparametric elements. Now the shape function, the very important part of our finite element method, shape functions. So if we can express displacement, sorry, so shape function, if we can express displacement at any point within the element in terms of nodal displacement, then the connectivity between them is called shape function. Okay, or displacement function or interpolation function. So u is equals to n into delta. So u is displacement at any point within the element, n is the shape function, and delta is the nodal displacement. So what we have told, if we express the displacement at any point within the element in terms of nodal displacement, then the connectivity between them is called shape function. Okay, so there are some convergence criteria that is used to define the shape function, or that is the requirement of the shape function. Okay, now we are going to place the relation between the displacement or nodal displacement. Okay, so there are some assumptions or there are some requirements for this. So what are those requirements? We'll see. So that is known as convergence requirement of the shape. So what is the convergence criteria for the shape function? In any acceptable numerical formulation, a solution must converge to an exact solution. Okay. The purpose of displacement function is to formulate the element stiffness matrix. As we increase number of terms, the system becomes more and more flexible, ultimately approaching the true flexibility of system. The displacement function should satisfy these following requirements. The first requirement is displacement field must be continuous. So this condition is easily made by polynomials since it is uh, the inherent nature of polynomials. Okay. Second convergence criteria is displacement must be computable between adjacent elements. You see this diagram. So what is shown here, that is adjacent element must deform without any gaps or overlaps at the common edge between two elements. Okay. And displacement field or displacement field for this first element is u is equals to n1 u1. For second deformed shape is n2 u2. Okay, n is shape function and u is displacement. Okay, and the elements which satisfy this requirement is called as computable or conforming element. Okay. Next next is third requirement is the displacement field must represent constant strain state of the element, CST. Okay, we have seen CST triangle, constant strain state. As we subdivide the continuum into smaller and smaller elements, these elements approach into infinite small size. The strain in each element approach a constant value. Therefore, it is necessary that displacement field must represent the constant strain state of the condition. Then, the displacement function must represent rigid body displacement. Okay, for example, one dimensional element we have du by dx is equals to minus ex, where ex should be constant. Okay, so what does this say? The displacement function must represent rigid body displacement for the element. So this expression is constant, is nothing but the representation of rigid body displacement. Next requirement is the displacement function must have number of terms or generalized coordinates equals to degree of freedom of element. Then sixth criteria is spatial isotropy or geometric invariance. This means that the displacement pattern this means that the displacement pattern should be independent of local coordinate system. This problem arises into two-dimensional element. Okay, so you, for example, uh, a1 plus a2x plus a3y, and v is equals to a4 plus a5x plus a6y. So this is the correct format. Okay, and what here they have shown, this is not correct. What is the difference between that? So we are going to use the polynomials in the system, in the generalized coordinate system only. Okay, so one way of achieving this isotropy is to consider the Pascal's triangle to assume displacement field. Okay, so these are the convergence criteria required for the uh, required to generate the shape functions. Next we'll see the Pascal's triangle. So this is most early asked question in exam, so it can be asked as a we have now online exam, so maybe we'll get one or two MCQs on this Pascal's triangle. So Pascal's triangle is used to achieve spatial isotropy or geometric invariance. The displacement should be balanced in x and y. So we should not include any term from one side of axis of the symmetry. So for example, cubic model of the following cubic model of the following is geometrically isotropic function. So u is equals to a1 plus a2x plus alpha 1 plus alpha 2x plus alpha 3y, like that. Okay, and we are going to uh, derive this element matrix in terms of constant strain triangle element. So here degree of freedom is equals to 2 divided by node in u and v direction. Okay, so this is the Pascal's triangle. So one so so this is the axis of symmetry. Okay, so all the elements in x y direction and all the elements considering y direction first and then second direction. So this is all the elements are symmetric. Okay, there should be balance between this Pascal triangle. So this is the Pascal triangle. So first we have shown here is the constant term, then second one is linear term, and then quadratic, cubic, quartic and quintic. Okay, so this is the shape of Pascal's triangle and this is the form of Pascal's triangle.